Welcome back, and off we go. So where are we supposed to start here? We're supposed to start right here. Okay. It was very strange. Supposed to start right here. How do we put a halogen on a carbon from an alkane? My goodness. Oh, that's the point of chapter 8, isn't it? Initiation, 2 propagation steps, heat, halogen. Oh, that's it. Br2, heat. Why the secondary carbon, not the primary? Because it's easier to generate a radical there. Now I got a secondary carbon with a leaving group on it. Now I'm going to do a lot of chapter 9 stuff. Anytime you see a leaving group, you got to think about chapter 9 options, don't you? So let's go downwards first. I got a moderate nu. I got a secondary Rx. Just finished a bunch of. All right. Secondary Rx. Moderate nu. Polar A product solvent. I got something saying I don't know, another thing saying I don't know, and the last thing says SN2. And I don't even have a stereo center showing, so you don't have to show me a stereo center. That's fair enough, right? Doesn't say it's worth 2 points either. So you're going to connect the CH3? Please don't. The nucleophile is the O minus. Show me you know that. The nucleophile is the O minus attached to a carbonyl that has a CH3. It's called acetate, isn't it? Up here, I have strong base plus heat. PKB. I know, you're used to alcohols being pKa 17. You're thinking PKB -3, 14 minus 17, but I'm just reminding you that ethanol and methanol really have a pKa of 16, like water. So -2. You don't, doesn't matter. Strong, negative. E2. So there's 2 products listed. Why do I think the product that goes in this box has a double bond between these 2 carbons? Because I learned a reaction that puts a bromine on one side of an alkene and an OH on the other. That's a good place to start with our logics. There's clues in these things sometimes, right? And you could do the E2 on the other side for the other product. Or I would also accept the Z version of the first product instead of the E. Both of them can get you to this organic halide here. How do you produce a halohydrin? Yep. Review reactions are always fair game. This is the nature of organic chemistry. Bromine and water. You can indicate that with adding H2O here or just saying AQ. That forms a vicinal halohydrin. If you're going to react this first one, this one to make that, you'd use HCl or the second one. That was our first reaction of alkenes. I just like to point out you'd make the enantiomer in equal amounts. But I only showed one of them because I wanted you to do an analysis on it like we did over here, but this time there's a stereo center. Let's start with this one. We have a strong nu. I'm keeping my color scheme from the previous page, so I don't have to write as much that way. polar aprotic again. Oh, yeah, polar aprotic. We have 4 of those to keep track of, 2 of them here. Acetone and dimethylformamide. Both of those say SN2. Please give me an SN2 product. Backside attack on a wedge bond gives a dash and pushes the H out front. And we have SH. SH in blue. And that's the end of that one. This one over here, I'm doing something with a tert-butyl O-. Oh. That was one of those ones where you see that thing and there's only one conclusion for that thing ever. E2. Strong, bulky base. Don't even need heat. In your notes, there's 4 of them. That's one of them. As soon as you see it, you think E2. And I want you to give me this one. And the minor, you might think I'd go with the same as this one, this or this, but then I'm looking ahead here and I need to make a terminal alkyne. And I don't know how to do that from this, the Z version of this in the box here. So don't do the Z version of that. Do this double bond. And then remember that we learned how to make alkenes into alkynes by halogenating them first. And then doing something we just learned again in chapter 9. And in the previous example, in fact, why don't we use the same base as the previous? Well, we could use the same base as we did in the previous example. Use an excess of it to do 2 eliminations. You're going to have a halogen on each side. You can do a elimination to make 1 pi and then an elimination to make another. You'd have a triple bond, but then you wouldn't have the C- at the end. So what I'm going to do instead is use a stronger base. I'm going to use KNH2 in heat. KNH2 excess and heat. Oh, I can't use K. I can if I cross this off and just do this. Do that on the test. I don't mind. Just say I'm making this. Spectators don't ever really matter. Strong base. I need it strong enough to take the H off of a terminal alkyne, because that's the 3rd thing that happens. First thing that happens with mole number 1 is E2 number 1 to make the first pi. Second thing that happens is E2 number 2 to make the second pi. Now you have a terminal alkyne with a pKa of 25. Third thing that happens with the 3rd equivalent or the 3rd mole of this is acid base. You get the terminal acetylide. And then I want you to say, oh yeah, that's a strong nu. See, I'm linking all parts of the course here. That's what I like about this stuff and probably what you hate about this. It's okay. You can be honest. R3-bromohexane. 3-bromohexane, R3-bromo. There's an H there, bromine there. And you're going to draw the black piece with a new bond here. Blue piece. 1, 2, 3, 4, 5, 6, 7. Don't do 7. 6. And make sure your stereo center is clear, or else I'm not going to be happy. It used to be R. It better be S when you're done. So what are we doing? 1, 2, 3. Oh, it looks like S already. I'm going to do this as a dash. And adjacent wedge. And now it's S. Yep. 1, 2, 3. And done. Done with that. Where'd this come from? It came from here. Where'd that come from? Here. Where'd this come from? Here. Where'd that come from? There. All right. Oh, yeah. How do you put an alcohol on there, an OH and an H on the adjacent carbon? Oh my goodness, we learned that a long time ago. And why is it relevant now? Well, we started chapter 10 where we're studying alcohols. It's very relevant to remember how we made alcohols in chapters where we're, using them and making them are all relevant. So that was our chapter 6 reaction to make alcohols, acid catalyzed hydration. And this is, what do you call it? When you take the proton off of an alcohol, it's called acid base. What do you call it when the product is NH3? It means the base was one that's already on the page in red previously, right there. Who cares about Na, right? Okay, acid base makes a strong nu. I think I lost my color scheme a long time ago. Strong nu should be blue. And then I changed my electrophile to blue. Let's get rid of that. And we're at R4 bromohexonine. My goodness. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. R means bromine here. H there. And we're attaching it to the nucleophilic O. Nucleophile doesn't change here. I don't know what to do with colors. Do everything in blue. This piece doesn't change. That's the attacker. The carbon that gets attacked changes. New bond to carbon number 4. 5, 6, 3, 2, 1, double bond. Make sure it's S. I didn't need to draw this. Just make sure this one's S. Right now it looks R-ish. Put the H on a wedge and it is S. Make that go all the way. Dash. Then we have this. Oh my goodness, what? This is the bonus round, this one. Yeah, I know I forgot this one. Sorry about that. But we're going over here and we're saying, okay, I've got this piece. It's right here. I got the O attached to a C with an ethyl on it. O attached to a C with an ethyl on it. Yeah, I got that. The C with the ethyl has CH2, CH2, CH2OH, CH2C. Oh, the only change here is I put an AntiMarkovnikov alcohol up there. It's a review reaction. How do you make an alkene into an AntiMarkovnikov alcohol? It's our old friend BH3. Is it fair to do all these review reactions? Oh, it's really fair if you're reviewing alcohol reactions on a test that has a chapter called alcohols in it. And yes, we made an alcohol. Anything related to alcohols is very good review material. And finishing up with not so good review material because it's chapter 7 stuff, but we should know for future that Na and NH3 takes an internal alkyne and makes it into a E alkene. And we got this, and then we got a wedge here and a dash here. Is that right? Yeah, it is. Stereocenter didn't change up there. Triple bond is now doubled. It's got new H's on it. You want to see them in green. One is to the left and one is to the right. It's E. I believe we finished this page. Is that a good stopping spot? I don't even know. I can't even remember how much time that took. There's not a ton here, although it looks like there is. Let's just do it. Provide a mechanism for each step below. These are all relevant. None of them is review. All relevant stuff. Let's do it. Here's a big clue. I need 2 initiation and 2 propagation steps to make an AntiMarkovnikov alkyl bromide. So let's do it like it's in the book. I've done it differently on the answer key, I'm pretty sure. And students have voiced their displeasure. So I'm listening. We had a NIT1 was to take a peroxide. And this is that less common radical reaction in chapter 8. And you make an alkyl oxide peroxide. And this is number 1 in NIT1, and in NIT2, you take that and react it with HBr. It's not an acid-base reaction, although it looks a little like one. It's got hooks. That's not acid-base. That's radical, dude. And that's how you generate your bromine radical to get your propagation steps started. Methanol is just a side product. We will not deal with him again. P1. Take your bromine radical. And this is a bromine radical that likes reacting with alkenes. Not taking H's. Not like the big reaction in chapter 8. It's not 6. This one hooks up with this end of the alkene and leaves behind a more stable tertiary carbon radical. So you've got your bromine on there. And it went on the AntiMarkovnikov position because it left behind a more stable tertiary radical that way. That doesn't look very radical, does it? That's my best. And P2, you take that radical you just made. That's how propagations always work, people. You make a radical in one propagation step, use it in the other, and then that next propagation step will make a new radical that gets used in the previous propagation step. And they cycle. Nope, not red. We made this radical here. The Br right there. It's going to react with the other non-radical, which was HBr. You still have almost all of your HBr left over because you only use a little bit with initiation. 99.9999999% of the HBr reacts this way. I don't know how to get that hook without intercepting other hooks. Oh, I think I did it. It picks up an H. Br dot is generated. What are you going to do with Br dot? You're going to use it in prop 1. And what else do you get? You get the product you have drawn on the top of the screen. For the product that was in the question, sorry. It's not drawn, it was provided. Done. And then you can continue for 1 point doing an SN2 reaction. I'm not going to write all these things down. They're not worth points, but that's a strong nucleophile, secondary carbon with a leaving group, and a polar aprotic solvent. It's SN2. Please give me an SN2 mechanism. Show me you know SN2 means backside attack. Show me that. SN2 means backside attack. SN1 carbocation. Burn those into your brain forever. There's your backside attack. There's your product right up there. We can draw it. Yeah, because on the test, you have to draw them again. You can't use the ones on the original handout. So to be fair, I'm doing what you have to do. I have SH. Hey, did you know that even without studying thiols, which we're not going to get to until after the test, I'm still working on what to do about that, You know thiols have a pKa less than 17 based on chapter 4. If that was an alcohol, it's pKa 17. It's not an alcohol. It's underneath on the periodic table. So I do expect you to know that's a pretty good acid if there's a strong base like hydroxide present. And there is. I do expect you to know an acid-base mechanism. It's just arrow from the lone pair to the sulfur in this case to make a S minus. I don't want to get rid of the top of the screen where I see the thing this thing has to react with. S minus is a strong nucleophile. Here's a primary carbon with a leaving group. Tell me you know that should be an SN2 reaction. And we got, what do we have? 3,3-dimethyl bromide. Or something with a different name. Doesn't matter. I just copied it from the top of the screen. I flipped it. Don't know why I flipped it. Backside attack, leaving group leaves. That arrow is got a huge head on it. Fix that up a little. And we make the other thing that's drawn at the top of the screen right there. I'll just copy it down here. We need to take a break soon, I know. Wow. 6 methyl sulfur, new bond to carbon that has CH2 bonded to C, double C with a couple methyls on it right there. Looks pretty weird, but that's it. And then HBr reacting in a normal fashion to go on the more substituted carbon. 3 points. I better see a carbocation here. Strong acids, alkenes. That was our first mechanism we ever learned. And do yourself a little favor and circle the stuff that's not going to change. Everything that doesn't have the alkene. Small favor. You can do that on your exam. The part you just wrote. Circle everything up to, I can't circle everything. Up to, but not including the alkene. Call it R. R is going to be bonded to C. That goes to a C like this. Need a cation because you put this new H over here. How did you do that? Pi electrons attacked the acid. Br minus left. Here's the Br minus. Need to have a lone pair and a charge. Some of you still think you can use the charge as a lone pair. That is wrong. Some of you still think you can leave the anion off and use the lone pair. This is also wrong. You get docked a quarter point each time you do that. They start adding up. Some of you will bear testimony to that fact. And what do we have? We have something that we probably need to draw because it's going to do things. We have this that's going to do this, which to me, after all my years of experience, is clearly an NGP because there's some kind of a intermediate carbons moved away from each other. This OH ended up here. Wow. We better draw it out. That's all I'm trying to say. Well, I got my circle here. Let's uncircle it. We got a cyclohexane that has a methyl on it. It's got a sulfur on it. It's got a bond to a CH2. C comes to a C with 2 methyls, and now we have a Br right there. This is a molecule, 1, 2, 3, 4, a molecule with a nucleophile and a leaving group. And that's how the O ends up on this carbon right here. I don't want to draw a bond there because that's less hindered than this one after you make a square. It's going to be a square 1, 2, 3, 4. So let's go ahead and do our NGP. You know I love NGP. It's on this video. It says I love it. I like arrows that end at carbons better. Square time. Sulfur. CH2 once, CH2 twice, C with a dimethyl, and a new bond right here. Sulfur, like oxygen when it has 3 bonds, is a sulfonium. Now the external nucleophile for the NGP is water. H2O is going to attack the least hindered carbon. Don't attack the carbon with the 2 methyls. It's too hindered. And don't have that arrow end at the cation. I'm still seeing students do that. They do this. Watch. I'm going to do it because I still see it. It makes me sad. They think the electrons go to the plus charge. They do not. They become a lone pair on the sulfur. The arrow, I'm going to exaggerate it this time, goes all the way to the sulfur. I don't want to see you keep losing the same points test after test for little things. Sulfur here is now still bonded. Here's the red bond to that. Still has the 2 methyls there. Has a CH2 here, has a CH2 there, and now has the oxonium created when water attacked the less hindered carbon. And what's going to neutralize our oxonium every time? Any chapter 9 reaction? Solvent. Use the solvent to neutralize the oxonium if there is one. Acid base never goes away.
Doctor, just a quick
yes.
question before we go on.
Go ahead.
Remember in the equation before, the H2O attacked the more hindered carbon.
Least the C that has no C's on it. This
Okay.
is the most the 2 possible choices are this one attached to sulfur or this one attached to sulfur. Why is this not a choice? Well, that won't open up the square if you attack that. You must open up the square, so you're down to 2 choices, this one or this one. Got it?
Okay, thank you.
You're welcome. It's a good question. And then we have sigma bond to a carbon with 2 methyls. Goes up to a CH2, goes to a C that has just an OH now, and that is just a slightly different version of what's drawn at the top of the screen, I hope. Oh, we're going to go real small. Not real big, real small. There and there. So sulfur goes to a carbon with 2 methyls. Check. Carbon with 2 methyls goes to a CH2, CH2. Check, check. Goes to an OH. Done. And yeah, that was another long segment. And we're going to pick up after the break. Where are we picking up with? I might have work to do. Oh, we'll see. I think I already have this one here. Oh, a good choice here. Now, the student that asked for this one also asked for another exams version where SOCl2 and pyridine react. I don't think we need to see it twice. It is an important reaction. We're definitely going to do a good job on it. But that's why I'm not going to pick the next one that they had on their list. We're going to go to, after that, I'm just doing a little preview. This is where I have to go to test 4 from fall 19 and find some multiple choice questions. So we'll pick up right here, and I will see you very soon. Bye-bye.